Good morning and welcome to webinar 11 in the Building Smart program. Today we're going to be talking about HVAC controls and equipment right sizing. This program series is brought to you jointly by Consumers Energy and DTE Energy. My name is Sonia Ponce and I will be your instructor today. Just a little bit about me. I've been in this business for over 20 years with a broad range of service, starting off in sales and moving into building performance improvement. One of my favorite things to do is to do training, particularly do code training, but also do training on a various number of topics related to the HVAC industry. Today, what I hope you get out of this session is to be able to explain how thermostats function, to be able to properly locate and install the thermostats and other HVAC controls, and also to be able to discuss the role of those thermostats and how they interface with the equipment, and then of course be able to talk to homeowners and potential clients about the benefits of right sizing equipment and how important that is to overall equipment efficiency. What we're specifically going to be talking about today, and before I get into that, I want to just mention that I do have my camera off. I'm probably going to keep it off most of the day today. I'm having some connectivity issues. I've been having connectivity issues. I normally keep the camera on just for the first couple of slides, and then I turn it back on at the end for questions. If we're doing okay with bandwidth, I'll turn it on at the end for questions. But right now, we're just going to leave it off. Today we'll be talking just a little bit about the history of thermostats. We'll talk about the progression up to wireless system capabilities. We'll talk about, again, right-sized equipment and controls for that. We'll talk a little bit about the difference between primary and secondary controls for HVAC systems, and then we'll talk about some requirements, some code requirements for those control systems. So let's just kind of dig in. So when we think about smart systems, or when you think about the word smart, the first thing you think of is obviously the human brain, right? This is processing a ton of information, much less so consciously than unconsciously, but again, still processing and taking a look at, over 1 billion bits of information per second. Smart homes aren't that smart, right? They aren't processing that much information, but they are pretty smart, right? They're processing about 1,500ths of a byte per second for information. This helps to enhance the home's comfort. It improves convenience for the homeowner. And ultimately, it reduces energy use, so it improves the energy efficiency. Overall, it gives the homeowner a much better experience in the space, right? Now, there are many ways that you can make a home smart. You can, for example, integrate things like health monitoring. This is a great thing for family members and caregivers if you don't live with a senior parent or something, right? This can include things like wearable pendants, so that if they fall, you can be notified. Motion sensors, so that you know where they are in the home, or carbon dioxide sensors, so that you can detect if there's an issue with the home. You might include things like a video doorbell, right, to alert you to visitors to the home, whether you're home or not. You know someone approaches your property. You might include cameras, and that can be, a security feature. You might even record some of this stuff. You could have this system contact emergency services or a family member if there were an intruder, or if there were a problem at the property. You might include things like smart locks, right, to control access to the house, or to help people who might be mobility impaired to get into the home without keys. Or if, say, you go out for a run, you don't want to have to carry, your keys and, a whole bunch of stuff. If you've got, smart locks, you can just, punch in your PIN and get into the home when you return. This also lets you know, who's in the house, who's not, right? You might include things like smart speakers, so that you can just speak controls, or that the homeowner can just speak controls or desires out. to a home system, such as Alexa or another controller. You might include things like media rooms. People are doing this these days, right? They've got media rooms in their homes that are almost as nice as what you get at the movie theater, right? Speakers and built into walls and things, and you've got stuff for gaming as well as movies and television and things like that. And of course, smart homes can incorporate heating and cooling, right? Heating and air conditioning. They provide they can provide a stress-free way of achieving higher energy efficiency, right? Reducing energy consumption. They can help achieve controlling various zones in the home. So homes can now be zoned similar to what we see in commercial spaces, where one room can be at one temperature, another space can be at a different temperature, right? Based on the needs of the occupants. So today, what we're going to be talking about primarily is that HVAC portion of the smart home. And so we're going to start the conversation off with, the brain or the control center for that smart home, which ultimately, resides with the thermostat, right? And the thermostat is this device that responds to changes in temperature or other indoor conditions, right? It could be humidity level built into the smart thermostat, but the basic thermostat itself is looking at temperature, right? And so it's responding to changes in the space temperature. Thermostats can be applied to a number of types of different spaces. Obviously, they can be, industrial processes. They can be applied to cars and things like that. But of course, we're looking specifically at buildings, right? And the spaces that the thermostat controls, these are called conditioned spaces. And so, like right now, where you're sitting, unless you happen to be sitting on your deck watching this presentation, you're probably in an office or either a home office or a commercial office space, right? And so you are sitting in a conditioned space. So let's take a look at just an abbreviated history of the thermostat as we go through this. So the invention of the thermostat is credited to a guy by the name of Cornelius Drebbel. He developed the first mercury thermostat to regulate temperature inside a chicken incubator, right? So the thermostat was comprised of a glass tube. It was filled with alcohol, and they had a little bit of mercury on top of that, and a metal rod in the mercury floating. When the heat of the fire in the furnace caused the alcohol to expand, it would push up the mercury with the rod floating in it, and that would then close a circuit that would lower a damper that would cut off the air that fed the fire. And then as the fire faded, the temperature in the box fell, and that way he was able to regulate the temperature in the incubator. For 200 years or more, thermostats were used primarily for industrial processes, right? In buildings and homes, temperature was primarily regulated manually. So when the fire got low, for example, a person would go put another log on the fire, or they would shovel more coal into the furnace. This often meant that rooms were cold in the morning if nobody was up throughout the night to stoke those fires. And the rooms kind of they had the potential of growing overly warm if the coals ran too hot. Now, around 1883, there was this professor, Warren Johnson, at State Normal School in Wisconsin. He had an early class in mechanical drawing, and he got tired of starting his days off in a cold classroom and leaving at the end of the day drenched in sweat. So he began talking to the stationary engineer into coming in early to stoke the fire, so that the classroom was warm when he got there. But then, of course, it got too warm throughout the day, so he would have to go back to the stationary engineer and ask him to, okay, can you pull things back a little bit? It's getting too warm. And he kind of got tired of going back and forth to the stationary engineer's office to ask him to, add more fire or reduce the fire. And so he began to pay attention to the temperature as it rose throughout the day. And so then he finally figured out, what was the best time or times to go talk to the stationary engineer. But he still, eventually got tired of running back and forth to that office. And so he then developed a thermostat that would ring a bell when it was time for the engineer to modify the temperature in the space. Right? He adapted a thermostat that had been developed by somebody previous to him, right? And then was able to, again, make some modifications to that so that it would operate the way that it needed to in order to ring this bell to let the stationary engineer know when to make some changes. A couple of years later, he filed for a patent, and that then sparked the beginning of what became the Johnson Electric Service Company, which we know today as Johnson Controls. Then there were some, let's say, some technology leaps, and we fast forward to 1953. There was this industrial designer, Henry Dreyfuss, who designed this round thermostat, which kind of became iconic, right? And this particular thermostat that we can see here, that it's got built into it, there's actually two thermostats there, and there are some red indicators here. So it's a day-night thermostat. This is a thermostat where the owner could set two temperatures and have a setback timer that would automatically switch between the two thermostats. Now, this thermostat had to be reset manually each day, though. This wasn't automatic. Right? So we were able to do some programming early on with thermostats, but it was still a manual process, right? These thermostats are similar to the thermostats that you may have seen in some older homes throughout Michigan. This iconic round thermostat. Some of the early controls here, obviously, it's got an on-off switch. You can switch, this particular model here can switch between cooling and heating, which was a later development, but you can see there's a set point adjustment here where we tell the thermostat what temperature we want to keep the space at. Here's a thermometer that tells us what temperature the space is actually at. And then here's a fan control, which either turns the fan off or lets it run in auto. In auto mode, the fan runs only when the furnace is, or when the system is heating or cooling in this particular case, and on runs the fan continuously. Just a quick note about that fan control switch. Oftentimes residential equipment, including thermostats, may be used in small commercial projects. Whenever you're doing a small commercial building with residential equipment, it's always best to keep that fan control in the on position, right, so that we get some continuous ventilation, similar to what we have with other commercial systems. Later on, we had the development or the introduction, if you will, of the thermistor, right? So this is a mix between it's a semiconductor, and it's a mix between a thermal control and a resistor. This can be used to measure temperature or to sense temperature changes and then to compensate for that. So with the development of this thermistor, we were then able to provide electronic thermostats, right? So we weren't using the mechanical thermostats anymore. We're using electronic thermostats. And there were several benefits to these electronic thermostats, right? They were smaller, they were more robust, they were more precise. So for example, with electronic thermostats, you can control within plus or minus 1 degree versus the plus or minus 2 or 3 degrees that you got with the electromechanical devices. They were also more flexible in mounting as well. They did not have to be level. The older thermostats, the mechanical thermostats, needed to be level because you had that mercury in there, that mercury switch. And in order for it to work properly, the thermostat had to be perfectly level. With electronic thermostats, you didn't have that mercury bulb switch. So they did not have to be exactly level, although you still want to keep them level for aesthetic purposes, right? But the electronic thermostats were really great for tracking and monitoring things. monitoring energy use. They did not have any droop. And they also were able to include additional controls, such as outdoor air temperature sensors, so that you could anticipate what the loads were going to be and make some changes in response to that. You also had increased security with some of them, because you needed to sometimes have a PIN in order to make changes to the thermostat set point. Some of the features with those thermostats, with mechanical thermostats and the electronic thermostats, one of the first things to be concerned with is the range of the thermostat. This is the range in which the thermostat is actually accurate, right? And this is noted by the temperatures listed on the face of the thermostat. So in this particular case, we can see here that although the values listed are from 50 to 80, this temperature is actually accurate between 45 and 85 degrees, right? Outside this range, it's not going to be accurate. For electronic thermostats and newer controls, we have similar ranges, but they for the newer controls, they are wider, right? The differential, this is defines when the thermostat starts and stops equipment. So this is the cut in and the cut out temperature. And typically for both heating and cooling, this is about a 2-degree span. So that, for example, if you're in heating mode, if the heating set point is 72, then if the heating set point is 70, then the thermostat would cut in at 70 and it would cut out when the temperature in the space got to be 72. Now, if you've got an automatic changeover thermostat, this could be a problem, where the heating set point and the cooling set point would have a space of overlap. So for example, if the heating set point was 72 and the cooling set point was 70, when the heating set point was reached, right, when the heating cutoff point was reached, the unit would shut off, but the cooling would come on automatically, right? And then cooling would run to its cutoff point, and then the heat would come back on automatically. So in order to avoid this, we've created a minimum interlock for auto changeover thermostats, and this is called a deadband. And this is a space in which neither heating nor cooling happens, so that there's no overlap. So if you've got this 3-degree deadband, you typically have this space here, this 1-degree space, where there's no heating or cooling, right? So we don't have the temperature, so we don't have the thermostats fighting one another, which helps to save energy. We also have to deal with anticipation or compensation. So when there's a call for heat, it takes the equipment some time before it starts to provide that heat. And during this lag, the temperature can drop another degree, so the room gets a little colder, right? And then after the equipment runs and warms up the room and turns off, residual heat in the system keeps on warming up the space, and the space could increase in temperature by another degree. And so when we add these 2 degrees to the differential, we now have a 4-degree temperature swing rather than the 2-degree temperature swing that we really want. So we add this anticipator in the heating circuit, or it's called a compensator in the cooling circuit, to reduce this mechanical differential, right? So it fools the thermostat into thinking that the space is a little bit warmer than it is, so that in the heating mode, it turns off a little bit sooner so that we don't have this overshoot. And in the cooling mode, it comes on a little bit sooner so we don't get as warm, so the space doesn't warm up as much. And that keeps the temperature swings in the space closer to that ideal 2 degrees, which is better for human comfort, right? It also helps to save energy. Around the 1980s, we began to see thermostats with digital screens that had both a date and a time in them, so that people could set temperature not only for the next day, right? We didn't just set them for what was going to happen tomorrow, but we could set them for every day into the future if we wanted. Right. So then we could program the thermostats, and homeowners could set the temperatures to fit their work schedules. Right. They didn't have to leave the heat on all day in order to be able to come home to a comfortable house, right? This was kind of the homeowner's kind of first introduction, if you will, to home automation, right? This is kind of where it began. So the idea of those smart homes. So here are some suggested thermal set points for those thermostats. We can see here that throughout the day we're changing the thermostat in the home, and we've got a temperature that we've got in the mornings, when we're when we're waking up getting ready for work. But then we can lower that temperature when we're away from the home, right? And it can stay low until we come back from work. And it can raise a little bit, and then it can go back down in the evening. We're very familiar with this with the Energy Star recommended temperatures for programmable thermostats, and we can program them for both heating and cooling, and then of course weekdays and weekends. And today we have thermostats that allow you to program for pretty much every day of the week if you want, every day of the year if you want. The initial programming for those thermostats, particularly for forced air systems, code requires that we have at least one thermostat per system. It requires that it be programmable. And while the energy code says that the interior design conditions should be 72 degrees for heating and 75 degrees for cooling, right? For design purposes, right? So for system sizing and design purposes, when we actually install that equipment and set it up and get ready to turn it over to the homeowner, we want to actually have set points of 70 degrees for heating and 78 for cooling, right? So this helps to encourage reduced energy use and gets the homeowner set on a path of a better sustainability, right? We also want to make sure that those thermostats have the ability to set back temperature set points either up for cooling or down for heating purposes. Again, when anybody might leave the home or not be there, right? Not be present. Thermostat wiring over the years has kind of become standardized in terms of the colors and what goes where, but color is not a rule, if you will. Each manufacturer may have their own preferences, so it's always best to label wires as well. Older models would have fewer wires. Newer models may have additional wires for staged cooling or staged heating. We've got a separate wire for the indoor fan. This allows the fan to operate independent of heating and cooling. Again, being able to keep that ventilation going 24/7 if we want, or at least throughout the workday if this is used in a small commercial application. And even in the home, for homeowners, as we begin to see, one of the things that we see with smart homes, if you will, what they're doing is they are bringing capabilities that have traditionally been used in commercial settings. We're bringing that into the home. So as we do, we want to be able to bring those control features too. So we want to be able to operate that fan. Operate that fan 24/7 or for longer periods of time. Some of the best practices for thermostat wiring, we want to make sure that our connections are tight and firm, that they're well established. We want to, again, make sure that we're labeling those wires. We want to make sure that we avoid things like splices, right? Because this can cause problems with, you might get shorts or intermittent connections. It makes it difficult to diagnose if you have a problem in the future. So we want to avoid splices. We want to make sure that, for example, staples, if we're using those in the system, that they don't puncture the wires. And since we all have cameras in our phones these days, it's a good idea always to take a picture of existing conditions if you're replacing a thermostat. That way you're very sure, you're positive of what wires went where. Today we have wireless systems. So we've progressed now from electronic to wireless systems. Now, with the wireless system, not everything is wireless. There are some pieces that still may require a wire, but the bulk of the pieces, particularly the communicating pieces, are wireless. And this is really great for any changes that need to be made to the system. for if you want to, if the homeowner may, for example, want to relocate a sensor or a thermostat or something, they can do that easily they can do that more easily with a wireless system. In terms of communication, you can get text alerts to either the homeowner or to their contractor, for example, if there's an issue with the equipment. You get automatic updates so that the software is always current, always the most efficient. Sometimes most wireless systems also incorporate machine learning, so they're able to save additional dollars by learning what the homeowner's preferences are. You can control accessories in the system. So, for example, you're not limited to just temperature, but you can control also humidity. You can control space, temperature, and conditions based on the motion of people within the home. Now, one of the things to be cognizant of when you have wireless systems is that controllers and receivers from different product lines, different manufacturers, they may be paired in different ways. With the advent of IoT, or the Internet of Things, right? You don't have to have one manufacturer for every component in your system. You can use different manufacturers. So you can use a Brayburn return air sensor, and you can use Honeywell, for example, room sensors. Right, so you want to make sure that you're following manufacturers' recommendations when pairing with other equipment, and you may also need to take a look at online videos or online resources to help with pairing that equipment. Wireless systems are also really great. That machine learning capability function with wireless systems is really great because a lot of people found the programming of the manually programming the electronic thermostats to be difficult or just to be challenging. There was research that showed, back in 2010, for example, that 89% of people who had a programmable thermostat were actually programming it. Today, those numbers are much better. Right, more people are using the programmable capabilities in their thermostats, but these wireless systems with their machine and learning and these smart systems with their machine learning make it, much easier for people to program their thermostat. So actually, the homeowner doesn't have to do that themselves; the machine does it for them. Right. Wireless systems also feature some new capabilities like geofencing. That creates a virtual boundary between the users, the homeowner, and a physical area. Right. So, for example, if somebody's got a smart device and it's connected to their geofencing in their home system, when their smartphone crosses a boundary, certain actions are triggered. Right. So the system then knows whether you're leaving or coming to the home. And it can then adjust temperature set points based on that activity, right? Based on the direction in which you're traveling. This is another feature that helps to eliminate programming, which again can be difficult for homeowners. It also means that there are no overrides. So if you've got it programmed to be off, or to be at a lower temperature that may not necessarily be comfortable during the day, but you come home for lunch or something, you would have to, if you with an older system, you might have to manually override that system so that it would, bring the house up to temperature while you were there. If you've got geofencing, you don't have to do that, right? So there's no more override requirements there. It also helps to improve the starting and stopping of equipment, again, based on the direction in which the homeowner may be traveling. Wireless capability also includes the smarter thermostats. Also include a lot of data for decision making, so it can help with monitoring. We can watch in real time what's happening with our thermostats, and we can actually the system can take action in the moment as things are occurring. You can also trend your data, so you can look at what has happened in the past and then predict what might happen in the future, so that you can predict what temperature might I need to have the house at based on what's going on right now, looking at how the homeowner required or requested these conditions based on something in the past, right? And of course, one of the great benefits of the wireless system is being able to get this information across all of your devices, whether it's a desktop computer or your smartphone or a tablet or what have you. Um, the enhanced communications with smart systems includes things like, of course, automatic software updates, so things are always up to date. Those text alerts and alarms, so you know what's happening while you're away from the home. One of the big things for convenience is this remote monitoring and troubleshooting. This is where the system can be monitored by a third party. That could be the manufacturer, or that could be some sort of controls integrator. And so that if there's a problem with the system, one, if they see, if they're trending data and they're looking at something and they see that something untoward is going to happen in the future, they can alert the homeowner to that. Or if the homeowner notices that there's a problem, they can tie in and call into, for example, service tech, and the service tech can look directly at the equipment and see what's going on. This can help reduce time on site for technicians who are coming to make repairs, right? So you can do that initial troubleshooting over the internet, over the phone, over the computer system, if you will, to see what's going on, and then make sure that you've got the right equipment on your truck or your van when you come out to the job site. If you have to come out to the job site to make any changes, you may be able to make some changes to set points or to control points remotely. Right. This is another capability that we see in commercial spaces that is making its way down into residential spaces. We have other things like demand controlled ventilation, dehumidification and humidification control. So, with these smart wireless systems, we're able to control not just the primary equipment, but at the touch of a button, we can also control auxiliary equipment, right? So air cleaners, humidifiers, things like that. We can also include hydronic systems. So in the past, smart systems, wireless systems, only addressed forced air systems for the residential market. Today, however, they do include hydronic systems. So if you've got a boiler, you can have thermostatic radiator valves that can be modulated, right, to decrease or increase the amount of heat output. These also can be tied to smartphones for monitoring energy use and tracking and data viewing and things like that. And you can also even zone these systems as well. All right. So again, having various temperatures in different spaces throughout the home. Both Consumers and DTE Energy have smart thermostat programs. Here we're taking a look now at what the Consumers Energy program looks like. This is their smart thermostat program, whereby Consumers Energy can make slight adjustments on select days or time periods throughout the summer, particularly when demand is very high, so they can modify the set points of your thermostat automatically. For the homeowner's participation, they get a $25 rebate and a $50 prepaid MasterCard. They get the $50 prepaid MasterCard when they first enroll, and then they get the $25 rebate for participating annually. And they can also, if they have a smart thermostat, they can use their existing smart thermostat. If they don't have a smart thermostat, they can purchase one from Consumers Energy's online store, and they get up to $125 rebate for that. To get additional information on the smart thermostat program, you can visit Consumers Energy at theenergyhub.com for additional details. DTE's program is called the Smart Saver program. This one is looking at managing energy use throughout the entire year. This one applies to both small to residential applications as well as small business applications. Of course, they just have to have Wi-Fi and central air conditioning or an air source heat pump. Here they get a $50 bill credit annually that is paid out in October of each year of participating. And you can visit DTEEnergysaver.com for additional details on that. So where is wireless capability going? What's it going to look like in the future? We aren't entirely sure, right? We're still, but we got lots of people working on this, right? Everybody's working on this. What we do know is that the capabilities that we see in commercial facilities, right, are making their way down into residential facilities. So we're going to see things like, full demand control ventilation. Right now, we have demand control ventilation, for example, in residential applications for kitchen and bathroom exhaust, right? But we might see, full, demand control ventilation. Last week we were talking about air systems, and someone mentioned that, well, we don't see often energy recovery ventilators being used here widely, right? They're used somewhat, but they're not used widely across the state. We may, begin seeing more of that with, of course, the demand control ventilation in the residential applications. You can do more indoor air quality monitoring, all sorts of things in the future with smart controls. Because we know that smart HVAC controls can help reduce our energy bills by up to 30% for the average Michigan family. And they can also, for example, increase home value, right? So real estate agents are saying that home value is increased by about, 10 to 15% with smart controls. Right. And, this, again, not just HVAC, but the entire range of smart controls. Smart controls make it more convenient for homeowners to manage that energy use. It provides individualization. So you can do zoning in homes that you traditionally have not seen. You've only seen that in commercial markets. You're able to integrate better, including those auxiliary pieces of equipment can all be controlled from a single network control point, right? So these thermostats are not just thermostats anymore, right? They are building automation systems, for the home. Some of the best practices for locating that thermostat within the space. We do want to make sure that we include, that we look for an interior wall. We want to stay away from corners and any airflow obstructions like draperies or appliances and things like that. We want to include it. We want to, try to place it as close as possible to return air grills, right? At the return air grill, this is the air that's going back to the central equipment. And this air has theoretically been very well mixed in the space. So you're getting a very accurate temperature reading for what the temperature is throughout the space, right? If we were to take, for example, if the thermostat were close to a supply duct, we would have a false sense of heat because that air coming out of that supply duct is actually warmer than the space temperature. So in order to make sure that we've got that good mix, we want to get, near the return air grills. We want the thermostat to be about 5 feet above the finished floor. However, if you've got people that in the home with that may be in, for example, a wheelchair or other ADA needs, you may want to lower that thermostat. So I think the ADA requirement for thermostat height is 48 inches, right? So we want to do that, and it may be lower. So if you need to, lower it to 44, you may have to lower it to 44 inches. You also want to avoid direct sunlight and electric lighting because these can present, similar to the supply ducts, these can present false senses of heat in the space. In addition to the thermostat, we may also see humidistat controls. We're seeing this more frequently here. We know that for ideal human health in indoor spaces, we want to maintain relative humidity levels between 40 and 60%, right? That's the perfect range for humans, and that's actually the range in which things like bacteria, viruses, and fungi do not like that specific range. They prefer that the relative humidity either be lower or higher than that, right? And so we want to, so we're beginning to see more humidifier controls that humidify and dehumidify, right? Um, there are various types and ways that we can control humidity in our spaces. Some are more precise than others. Human hair humidifiers, that's a pretty old technology, but it actually still is used. We see that in some mostly commercial spaces, but that technology can be used in the home as well. We often see it in humidors, right? So people that may have an in-home system to maintain the humidity for their cigars, right? We may see that there. There are also the nylon metal humidifier control, which is a similar control to the bimetal control of the mercury thermostat. So here, instead of having two pieces of metal that are bound together and that expand or contract to actuate the controller, here you've got a piece of nylon bound to a piece of metal that expand and contract at different rates to actuate the device. And then, of course, we have electronic humidifier controls as well. Whether you've got a simple thermostat or a humidistat or a full-blown wireless system, we want to make sure that that the homeowner is aware of the maintenance requirements for this system, and we want to make sure that, for example, these are being looked at, annually. So we want to have, a service provider perhaps come out, regularly to take a look at the system and make sure that things are working properly. Right. So when you are performing maintenance on the HVAC system, you also want to look at not just that primary equipment, but you want to look at the controls. You want to make sure that those terminal connections are tight, that they are firm, that they are solid. You want to make sure that the contacts are clean. And one of the things that we often don't think about is the calibration of that thermostat on the wall. Right. So oftentimes, most times, the thermostat is just placed directly on the wall. You may not want to do that. You may want to have a buffer between the thermostat and the wall, a thermal buffer, right? So that it's not directly up against the wall and measuring wall temperature. So it's a little bit off of that so that you do have airflow around the entire unit. And then you want to make sure that it's calibrated so that the temperatures that it is reading are actually the temperatures that are actually in the space. Even with the best of maintenance, you can still have problems with equipment. These are some of the signs that you might see of poorly operating controls. Controls might be operating poorly for a number of reasons. It could be sometimes it's operator error, sometimes it's programming, right? Sometimes it's the location of the piece of equipment. Sometimes it is the device, right? But if the homeowner experiences any of these situations, right? The display temperature is not matching the room temperature, or the space and the thermostat saying the space is 70 degrees but it's really cold in here, or it's really hot in here, or if this display is unresponsive, right? These are indications that there's something wrong and we need to go back and take a look at some things, and do some troubleshooting. When we're doing troubleshooting, we want to make sure that we don't just go straight to the equipment and start working on it. We also want to, have a conversation with the homeowner. You want to ask them some questions about how the system is working. What is their experience with it, to give you an idea of what might be the source of the problem. Right. So but some of the things you want to look at, is the thermostat level and plumb, right? Again, for older thermostats, this is really crucial. For newer thermostats, not so much, but still a good idea. right? You want to look at the voltage of at the thermostat. This could impact the anticipator and cause things to be overheating. You want to look at, where is the thermostat located? Are there any faucets and sources of heat or cold that may be impacting the operation of the thermostat? Is the wiring correct? Is it in good condition? Are there any design issues? For example, are there any leaky ducts, or is there a clogged filter perhaps? Or what often may be the case, is the equipment properly sized? We talked a little bit about sizing in the past, but um, code requires that HVAC equipment be sized in accordance with these two manuals from the American Contractors Association, or the Air Conditioning Contractors Association of America, my apologies, to make sure that the equipment is not oversized, right? This is important this applies to both heating and cooling equipment, as well as humidifying equipment. We want to make sure that the equipment is going to be able to deliver optimal comfort to the homeowner, and it can't do that if it is oversized or undersized, right? So undersized equipment, the equipment is too small for the space. It's not going to be able to, for example, reach its set points. The equipment, they may then, run longer than it has to. So it's not going to achieve set point. It's going to keep running, and that's going to waste energy. With undersized equipment, you also might experience higher humidity levels in the home. So you may end up with mold or mildew in the space. You get these higher humidity levels because the equipment can't cool as much as it needs to for the space, right? And that cooling action of the HVAC system actually is part of what helps dehumidify in the summertime in particular. Right. And so if you've got higher than desired humidity levels, then you've got too much moisture in the air. And again, you run into problems with mold. This could impact, your indoor air quality. If you've got people in the home that, for example, have respiratory illnesses, asthma or allergies, things like that, those could be exacerbated by the poor indoor air quality and specifically higher humidity levels. You also get, more wear on the equipment because it's running more often than it needs to. This is going to cause premature failure, potentially, of the equipment or of certain components. And of course, all this leads to higher energy bills. If the equipment is oversized, it's too big, then you're going to have short cycling. The equipment's going to turn on and turn off a lot frequently. It's going to do that more often than necessary, right? So you're going to have higher energy bills as well, because when the equipment starts up, it's drawing more energy than it does when it's running at steady state. And so that's going to increase energy use and cost. You also have the starts and stops create additional wear and tear on equipment. So this is also going to lead to premature equipment failure. And you're going to have higher humidity levels with oversized equipment, just as you do with undersized equipment, although the reason is a little bit different. With undersized equipment, you have higher humidity levels because the system's not able to cool sufficiently. With oversized equipment, you have those higher humidity levels because the equipment is not running long enough to cool the space and dehumidify. So whether the equipment's oversized or undersized, you're using more energy and you're putting more wear and tear on the equipment than is necessary. So you want to make sure that the equipment is right sized. When it does this, it's going to last for the expected lifetime. It's going to run efficiently, and it's going to use the least amount of energy, right? So the homeowner will then get the most out of their air conditioning system, out of their heating and air conditioning system. Now, up to now, we've been talking about the primary controls for your HVAC system. HVAC systems also have secondary controls, right? So those primary controls are those controls that start and stop the primary equipment. Those secondary controls are what regulate the equipment and then protect both the equipment and the home from various things that could happen during a failure. So some of the secondary controls, again, these are the things that are metering and monitoring and protecting equipment. So for example, they may manage the flow of air or refrigerant. They may manage air pressure in the ductwork. There may, for example, be a timer to protect, to help protect the evaporator coil from freezing, right? So your defrost cycles on your heat pumps, right? They're going to have timers associated with them. This is one of those secondary controls. Some other secondary controls there might be in place to shut down the equipment in the event of adverse conditions, or for example, to make sure that there's airflow before burners start, right? So this is protecting the equipment. So code requires often that there be some of these secondary controllers in place. One of them, some of them are integral to the equipment, and some of them are external installed in the field. So one of them, for example, is this duct heater interlock that requires that the fan be interlocked with the heat within a heater, so that you don't have heat operation when the fan is not operating. So this is something that you might see internal to a forced air furnace, but if you add an additional type of heater into a space, into ductwork, for example, you want to make sure that you have this interlock in place. Water level monitoring is one of those mandated controls as well. This is a sensor to prevent drain pan overflow, which could result in property damage, right? So this is this water level monitor is a code requirement. We may also sometimes have to have an auxiliary drain pan, right? If there's the potential for water damage, if we've got a piece of equipment that, for example, might be located in an attic space, we want to have this auxiliary drain pan in case the primary drain pan that came with the piece of equipment that might be internal to the equipment gets clogged or overflows. If we have this additional drain pan, we want to make sure that it drains to a space that is frequently seen, right? So to a drain or a sink that the homeowner may see on a regular basis. Something, for example, like in the laundry room, or where they may go frequently, so that they can see that this pan is draining, right? That lets them know that the primary pan is backed up and there's a problem. Now, of course, if you've got some smart controls, there's probably something in the controller that's got a little red light flashing or letting the homeowner know that this is a problem as well. But we still want to have that backup system. We want to have condensate pumps with systems that where we're going to have condensation. We want to make sure that these pumps are not just wired to come on when we have condensate and we need to drain that. We also want to make sure that these are wired such that they prevent the equipment from operating if this pump fails, right? So this is a fail-safe switch for the equipment, because if the condensate pump failed, then we would get a backup, we would have water damage, and we don't want that to happen. We don't want the primary piece of equipment, the furnace, to be operating if the condensate pump is not operable. There may be dampers in the system that need to open, for example, when the exhaust system is operating. So if you've got a kitchen or a bathroom exhaust system, you want to have dampers that open when those systems are operating, but that close well, close tightly when those systems are not operating, so that you don't have infiltration or exfiltration from the space. Whole house mechanical ventilation systems are required to have overrides, right? So there may be an emergency situation, or there may be a need to make a temporary adjustment to those controls. And so we want to make sure that the homeowner is able to do that. So in addition to having the auto control that may be at that central brain, right, that central thermometer, the thermostat controller for the space, we want to make sure that there's an override switch for that as well. For those of you who are more interested in controls for smart homes, you may be interested in joining the Custom Electronic Design and Installation Association, CEDIA. They have an annual conference. This year, their conference is next month in sunny Colorado. And it will feature technology seminars as well as training courses for certification in smart home integration. CEDIA is a trade association, so it's not a specific business. It is a trade association. They focus primarily on smart homes, smart home technology. They represent manufacturers, designers, integrators, and they offer certifications for integrators and other professionals in this field. They've been around for a number of years. Some of the certifications that they offer, certified cabling and infrastructure technicians, certified integration system technician, electronic system certified technicians, networking specialists, and designer. So they offer electronic system certified designer accreditation as well. There are a number of CEDIA members across the state. I don't know of any local meetings. I actually was not familiar with CEDIA myself. This tends to be more so on the residential side, so this is not something that I was familiar with prior to preparing for this seminar. But it sounds very similar to ASHRAE, so I'm going to compare it to ASHRAE for the homeowner or for the residential market, if you will. And sounds like it's going to be a really great program for their September session. With that, I'm going to pause and see if there are any questions, and I will turn my camera back on. But before I do that, I'm going to move to the next slide. So, and just let you know what's coming up next week. Next week, we'll be talking about electrical systems, primarily lighting, and we'll be talking about non-comfort HVAC applications. So we'll look at things like pool heaters and saunas and snow melt systems and things like that for the residential market. And with that, I'm going to kind of pause here and just see if there are any questions. We'll just kind of hang out for a bit. And let me turn my camera on. And we'll just kind of see here if there are any questions that anybody might have. If not, I may scroll back through and see if there's anything else that I didn't thoroughly discuss in any of the slides, but I think that I did. Let's see here. There are no questions. Are you sure there are no questions? Not even one. Let me see here if there's something that that we can chat about. I don't know if we can do a question on the fly, John, or a poll question on the fly for the audience, but we've just got 1 minute left here, so I'm going to just kind of, again, keep hanging out here and seeing if there are any questions that that anybody might have about the HVAC controls. One of the interesting facts that I found, I'm just going to share this with you, that I thought was really interesting as I was preparing for this seminar, was how early on things like programmability were integrated into HVAC control. So even though we've only been seeing that in the residential market here, in the last 20 or 30 years, widespread. When HVAC equipment was first introduced into the home market, and in the late 1800s, when Warren Johnson came up with his thermostat, we had programmability in those residential thermostats, it was mechanical, but it was programmable. And I don't know why, but I'd be very interested to look at why we eventually got away from that. I wonder if it was just considered to be too difficult. I would imagine that it perhaps was similar to the challenges that we saw with the introduction of the programmable thermostats um, in the 1980s, and just homeowner reluctance to use the technology because they found it a little bit challenging, a little bit too difficult. And so we're cycling, I guess, back to that. And now we have these smart thermostats that have taken that burden away from us. We don't have to do that. Um, and so we're at time now. So I'm going to go ahead and wrap this up by saying that this has been a session on smart thermostats, controls for HVAC systems, and right sizing the HVAC equipment. There are a number of online resources and manufacturer sponsored resources to gain more information in this area. And as this technology is rapidly changing and rapidly expanding, I would encourage you to stay close to the manufacturers who are in this industry and that are coming out with new advancements almost daily. With that, I will say thank you so much for attending today, and please have a great day. Goodbye.